In step 4, our attention is turned to objective function. We need to figure out ISO line based on the objective function. If the objective is to maximize profit, we call those lines as ISO profit line. If it is to minimize cost, we call them as ISO cost line. In details, we need to, first pick any two different numbers as the reference. For both numbers, we draw the respective lines that represent the objective function equal to them. Those are two ISO lines corresponding to different objective values. Then we need to determine the right way for moving the ISO line. If the objective is to maximize, then it must be from small number line to the big number line. On the contrary, if we want to minimize, then it must be from big number line to the small number line. Now, in our example, this is our objective function, z equal 400x1 plus 800x2. Let z take the value of 800k dollars, and we try to draw the ISO profit line representing all the profit, all the possible combination of max and max, which generate the total profit of $800,000. Again, this can be done by finding and connecting the intercepts on each axis. Suppose we try to get such profit by producing no max, so let x1 equal to 0. Then we need to produce 1,000 of max, since each max contributes $800. That gives us the first intercept on x2 axis. Then switch to x1 axis, this time produce no max, and the x2 equal to 0. We will need 2,000 max to get that $800,000 of profit, since max unit margin is only $400. We can correspondingly mark out the second intercept on x1 axis. Draw the line across the two intercepts. This is our first ISO profit line. Now, we are ready for the second ISO profit line. This time, we pick a reference profit of 1,200K. By the same procedure as before, we first figure out the first intercept on x1 axis by assuming all the profit is from max. And we next get the second intercept on x2 axis by producing only max to reach the targeted profit. Now we can draw the second ISO profit line through the two intercept points. The second line is a higher profit line. Hence, when ISO profit lines are moving upwardly, z, the profit objective value, also increases. If moving them downwardly, z decreases. So the right direction must be upward. Finally, we get to step 5 to find out the optimal solution. Okay, it depends on moving the ISO lines in right direction and move it as far as possible so that Any further moving will make the iso line totally go out of the visible region. The final touch to the visible region typically happens at a corner point. So based on such corner point, which must be an intersection of two constraint lines, we can solve the equation to figure out x1 and x2 and the resulted objective value. Those are the final optimal solution of the linear programming problem. For our example, let us put both visible region and iso profit line in one graph. Okay, we need to move the iso profit line upward as much as possible within the visible region. Now the corner point A is reached. Should we move in the iso profit line further? Yes, since there are still ahead shaded areas above the iso profit line. Now the corner point C is reached. But we should push the line up further since we still see the shaded visible region above the current iso profit line. This time, the corner point B is reached. Should we move up the iso profit line further? No. If we keep moving, iso profit line will have no connection to the visible region anymore. So we must stop pushing up the iso profit line once it reaches the corner point B. And the B is our optimal solution. A very important property of linear programming solution is that if there is the solution existed, then the optimal point must be on one of the corner points. Let's figure out the numerical values of the optimal point. We know B is the intersection of testing constraint and assembly constraint line. So we can compose the equations group corresponding accordingly. To solve this equation group with two equations and two unknown variables x1 and x2, we start with the assembly question. Moving 4x2 to the other side of equal sign, we have x1 equal to 3000 minus 4 times x2. Plug such relation into testing equation. That is, replace x1 in testing equation with the 3000 minus 4x2. We have the equation on x2 only. Multiplying 3 into the parentheses, we have 9000 minus 12x2 plus 5x2 equal to 5000. Deduct 5000 on both sides of equal sign. We can transform the equation to 4000 minus 7x2 equal to 0. Now, it is easy to figure out. x2 is equal to 4000 divided by 7, which is not an integer number. We will round it to the closest integer, 571, and plug it back into testing equation to solve out the corresponding x2 as 715. Clearly, we can see at such solution, both testing and assembly resources are totally used up. Hence, we call both resources binding resources. Plug the numerical values of optimal solution into the objective function, we can calculate the resulted total profit. This is the optimal profit. That means this is the best outcome you can have. No other production plan can make a higher profit than this one. Before we go to talk about the Excel approach for solving linear programming, let me introduce some special cases you may see in a linear programming solution. Here is the full list. Special case 1 is that you may find some constraints are redundant. If you drop them, the feasible region won't be affected, and so is the optimal solution. In special case 2, you will find the optimal solution is not unique, as in the previous example. What happened here is that the iso line derived from objective function is parallel to one border of the feasible region. So the final touch to the feasible region is not just one corner point, but a line segment. Of course, any point on this borderline will give the same objective value, which is also optimal. In special case 3, you will find that the optimal objective value is unlimited. Basically, we will have an unbounded feasible region like this one. On one direction, it can be extended forever. And at the same time, you want to maximize the objective function. The right direction to move the isoprofit line is the same to that forever extended direction of feasible region. So you can forever push up the isoprofit line to the infinite large number. In special case 4, you can find there is no solution at all. This is because the constraints are self-contradictory, so that no feasible region can be characterized. For instance, third constraint requires the area not containing the original point, but both first and second constraint requires the area to have original point. So you cannot find any region which both have and not have the original point. This feasible region must be empty. Correspondingly, you cannot find the solution too.